CU Boulder's involvement in drone research, you can really trace back to the mid 90s when I met a person I knew from the National Severe Storms Lab from Norman, Oklahoma. We ran into each other at the National Center for Atmospheric Research one summer, and I think it was 1995. And we started discussing a project. It's called Tornado Chaser. And that project culminated with in the late 80s with the building a small drone that was flown, but it was never operational. And so I said, well, let's get this restarted at CU Boulder. We made a deal to do that, and I got things started. This is about 1995, 96, a series of student projects. We're looking at taking the design and advancing it with the intention of developing a drone that would then be used for severe weather research. Around 2000 or so, we started making some progress with some really good students. And then in 2003, we created the Research and Engineering Center for Unmanned Vehicles. So the early days of our drone research, the motivation was initially to explore severe weather with a legacy that goes back to the University of Oklahoma. Once we started to demonstrate some capability, the Air Force got wind of some of the research that we were doing. And then after the U.S. invaded Afghanistan and later Iraq, we had a project that the Air Force Big Safari program came to us to task us or to ask us if we could develop a test bed to test the idea of using small drones to support communications networks. And so this was around 2003, so right about the time that the Research and Engineering Center for Unmanned Vehicles was created. And in 2004, we made the first flights using UAS drones that we built in-house. These were fixed wing, weighed about 25 pounds, had gas engines, 5 horsepower gas engines, and could fly on the order of an hour. And each of these aircraft carried a single board computer that matched the computers that we also had on the ground with radios and in vehicles and cars on the road. In 2004, we did the first flights flying as many as 3 drones at one time with cars driving between Boulder and the town of Lyons, which is a few miles north of Boulder. And we demonstrated that the drone network could support voice over IP phone calls between 2 callers with the signals being routed through the drones. After demonstrating that capability, of course, all along we were thinking this is a dual use technology. This is the type of technology that can help us advance atmospheric research with drones. And so our Air Force sponsors were very amenable to allowing us to use the fleet to do some early experiments with atmospheric sensing. And so that was how we then started to make a crossover to then adapting the technologies that were supporting the mobile communications for the Air Force to supporting mobile sensing for atmospheric research. And so this started to happen between about 2007, culminating in 2009, when we did the first intercepts of thunderstorms with small UAS. And this happened in the Pawnee National Grassland in northeast Colorado, along with our meteorological colleague from the University of Nebraska-Lincoln, whose name is Dr. Adam Houston. And we demonstrated the ability to explore air mass boundaries that are formed when thunderstorms are passing through an area. And we did this in the fall of 2009. And then the largest tornado research project to date, which was called Vortex 2, that stands for Verification of the Origin of Rotation in Tornadoes Experiment, number 2, the second experiment. That was conducted in 2009 and 2010. And we then were able to deploy the Tempest UAS to make the first supercell intercepts with a drone, a small drone, and actually a tornadic supercell that was out on the eastern Colorado plains. During that second period, the period where we were starting to do mobile sensing, for atmospheric science, we were working closely with the FAA, the Federal Aviation Administration. I first approached the FAA in 2004 with a plan to enable us to do mobile uh, sensing using drones to explore severe weather. And I recall that meeting, and the person I was talking there at FAA, he said, "You want to do what?" And so that was kind of the start. And so, but we worked with the FAA very closely, and and they worked with us to develop provisions that were provisions, meaning basically instructions that we would follow that then allowed them to issue us a certificate of authorization to conduct our operations according to their provisions. And we started off with 59 separate certificates that allowed us to operate in a relatively small area of the Great Plains in northeast Colorado and uh, northwest Kansas. And so uh, after the intercept of supercells in 2010, the research moved into a different phase that led to the creation of Iris. We had some real capabilities at that time that we could really do atmospheric research like no other group, essentially in the world, with small UAS. The mobile sensing that we were doing, it allowed us to do targeted observations. In other words, you go out and you see a storm and you release a balloon. You hope that balloon goes into the storm or goes where you may want it to go. And oftentimes it won't, because if it's released near a downdraft, it's going to blow away from the storm rather than in the storm. And these storms move. Uh, and then sometimes they move quickly, 30, 35, 40, 50, 60 miles per hour. And so if you want to explore or examine what's going on with these storms, you have to target them and be able to track them. In 2015, CU Boulder campus, the chancellor put out a challenge to the campus for the Grand Challenge, the CU Grand Challenge. And that was inspired by President Obama, who challenged universities and industry to conduct research to address the grand challenges. So I led a group that put together a proposal to establish what we call IRIS, the Integrated Remote and In Situ Sensing Program. And that was one of the two original selections for a CU Grand Challenge. So starting in 15, IRIS was kicked off with a significant investment from the campus, and we were able to create infrastructure that included vehicles and additional aircraft that then really put us in a situation where we could really develop capabilities that were going to be useful to atmospheric scientists. And that's when the Raven then followed. Prior to the Raven, the Twister, which was a more advanced version of the original Tempest that flew into supercells in 2010. The Twister had two motors on it instead of one, enabled additional performance. And then the Raven came along in 2019 to support Taurus, the targeted observation with radar and UAS of supercells. And again, that was led by our colleague at University of Nebraska-Lincoln, Adam Houston. Our drones were to be the pivot instrument in that project, meaning that when we would target a storm to observe, the instruments were to be turned on simultaneously. So the idea was to make simultaneous observations of a single storm with drones, radar, mesonet trucks underneath it, everything, even a hurricane hunter. We actually had a hurricane hunter that was part of the team, and we coordinated the Raven flights with the hurricane hunters so that they knew where we were flying, where we were flying at the same time that they were. And so we maintained a 2,000-foot separation between our operations. And so we literally were flying with coordination with the hurricane hunter for the Taurus 2019 field campaign. So that shows you there how far we had advanced, where we went from RC airplanes that could barely fly in the late 90s to where a hurricane hunter was coordinating with us to fly in the same airspace where they flew around the storm and we flew beneath the storm for coordinated observations. And that was in 2019. And we have continued to develop those capabilities since. What has changed the most over the past 30 years, it is the mobile communications and computing. So that enables us to to be in control of the aircraft while we're moving and the aircraft is moving. So when I say while we're moving, meaning the ground station is moving and the aircraft is also moving, or multiple aircraft actually in some instances. The computing capability has allowed us to deploy aircraft with increasingly autonomous systems. So rather than flying the aircraft manually like we have in the past, the aircraft have autopilots that interface with a flight computer in which we, or I should say, usually our students, who are usually the pilots, they can command through the flight computer, which then is controlling the autopilot. So it's talking to the autopilot, and the autopilot is what is actually controlling the control surfaces that enable the airplane to fly where we want it to fly. And typically that means flying from one GPS waypoint to another. And so we don't actively fly the airplane between the GPS waypoints. It flies itself, or the autopilot, I should say, flies the airplane. So if I were to describe the evolution of drones and the drone research that we have conducted in that to date, I would describe that in four phases or four eras. The first phase was really where we were attempting to construct remote control aircraft that to fly manually. So meaning that someone was standing with a joystick and flying the aircraft uh, and trying to get into weather phenomena. The second phase was the phase in which we received funding from the Air Force to develop mobile communications capabilities with small drones. That also was a phase in which we were able to build aircraft that would carry significant payloads, including computers and radio equipment. The third phase was one where the regulatory part of the capabilities also was being advanced. And so in that phase, we were then starting to do mobile communications and mobile sensing that was based on mobile communications, and also getting FAA permission to fly in various parts of the national airspace system, primarily over the Great Plains of the United States. And then the fourth phase, the phase that we are currently continuing to expand, took the mobile sensing capabilities, and we're able to refine that into a targeted observation capability, meaning that we now, working with our meteorologist colleagues, for instance, they can identify phenomena that they wanted to investigate. And these phenomena don't stand still. They're in the atmosphere, so they're moving. And so with regulatory clearance, we're able to now get in close to these storms, follow them, sample them as they evolve and move, which has culminated in projects such as Taurus, where we were sampling what's called the left flank of a supercell, and then more recently the ice chip campaign, in which we literally are flying as close as we can on the back end of a supercell or a storm, producing hail, so that we can capture the swath of hail on the ground right behind the storm. And so that is how some of the major advancements have happened over the past 30 years.